Now we are going to look into another kind of improper integrals that we will refer to as type 2 improper integrals. And to illustrate what it is, let's start with this definite integral of 1 over x between -2 and 1. Then it might be tempting to say, well, I know an antiderivative of 1 over x, it's natural log of absolute value of x, and so all I have to do is evaluate this antiderivative between -2 and 1, and when I plug 1, I get ln of 1, which is 0. When I plug -2, I get ln of 2, and therefore this integral has value negative ln of 2. That would be tempting, but that would be a mistake. And the reason is that here, when we write this equality that we have just crossed, we are using the fundamental theorem of calculus that states that if you have a function that is continuous on an interval ab, then to calculate the integral from a to b of that function f, all you need to do is find an antiderivative of f on the interval ab, and then plug the value b and the value a and take the difference. But the key assumption here is that the function is continuous on the interval. In this case, 1 over x is not continuous on the interval -2, 1. If you take a look at the graph of the function 1 over x on that interval, it looks like that, and you see that we have a discontinuity at 0 where the values of the function go towards infinity. And so here there is a problem, because in particular we cannot use the fundamental theorem of calculus on that interval that contains 0. However, if I pick a t, say, that is less than 0 and greater than -2, then I can surely integrate the function from -2 to t using the fundamental theorem of calculus, because the function is continuous on that particular interval. So here I get some integral. And then I can look at what happens when t approaches 0. And hopefully, if there was a limit, then that would be the only way to define the integral from -2 to 0 of dx over x, would be to take this limit of the integral from -2 to t as t is approaching 0 from the left. Now, to define our integral from -2 to 1, or try to see if there is a way to define a value for it, we would have to do that, and also do the same thing from the other side. In other words, integrate from t to 1, and then let t approach 0 from the right. And then we would define the integral from -2 to 1 as the integral from -2 to 0 plus the integral from 0 to 1, where both integrals here are in fact also improper integrals and defined as limits. The first one is a limit when t is approaching 0 from the left of the integral from -2 to t, and the second is the limit when t is approaching 0 from the right of the integral from t to 1. Now in this case, if we try to calculate the first integral, the integral from -2 to 0 as a limit, on the interval -2 t, the function 1 over x is continuous, so we can use the fundamental theorem of calculus on that interval. And so our integral is really just the value of ln of absolute value of x at t minus the value at -2. And therefore we obtain the limit at 0 of ln of absolute value of t minus ln of 2. Since the limit at 0 of ln of t, 0 from the right, but here we have the absolute value, so it doesn't matter from which side we approach 0, it's going to be from the right anyway. The limit of natural log at 0 from the right is -infinity, so this is what we obtained for the limit. So one of these two integrals is already divergent, and therefore this integral is also divergent. Now so improper integrals of type 2 are improper because we have a discontinuous integrand. In other words, the function that we are integrating has a discontinuity in the interval of integration. The first case we're going to look at is a case where the only discontinuity is the right endpoint of the interval of integration. So in this case, b. And then we're going to define, just like we have on the previous example, define the integral as the limit as t is approaching b from the left, so that t is approaching b from the inside of the interval, of the integral from a to t of f of x dx. Because the function is continuous on the interval except at b, the function is continuous on the interval at, and so the integral from a to t is well defined, and then we can look at whether we have a limit as t is approaching b. If there is a finite limit, then the improper integral is convergent and takes the value that is equal to the limit. If this limit does not exist, in particular if we have an infinite limit, we say that this improper integral is divergent. So when b is a discontinuity, this is how we define this improper integral of type 2. In the case where the only discontinuity on the interval ab is a left endpoint, in this case a, we're going to similarly define the integral as the limit as t is approaching a from the right, so again from the inside of the interval, of the integral from t to b of f of x dx. Again, if t is greater than a, then the integral from t to b is well defined because the function is continuous on the interval from t to b. Then we take the limit of these integrals as t is approaching a, and if we obtain a finite limit, then this is the value of the integral and the integral is convergent. If we obtain an infinite limit, the integral is divergent. So if a is a discontinuity, the only discontinuity, this is our definition. And now looking at the case where we have a discontinuity that is an interior point of the interval of integration, we're going to, and of course we need the discontinuity to be isolated, in other words to have only one at a time inside the interval. Then we're going to define the integral from a to b as the sum of the integral from a to c and the integral from c to b, where c is our discontinuity. Of course, this is itself an improper integral that is defined via the first case, and this is an improper integral that is defined via the second case. So for this to converge, for this integral from a to b to converge, we need both pieces, both integral, to be convergent. If one of them is divergent, that's enough for this integral from a to b to be divergent. Now let's go through a few examples to see how we can decide whether these kinds of improper integrals are convergent or divergent, and when they're convergent, find the value. We start with the integral from 0 to 3 of 1 over x root x. So the first thing is look for the discontinuities of the function in the interval of integration. In this case we have 1 over x to the 3 half, so that's going to be continuous everywhere except at 0, and 0 is precisely the left endpoint of the interval of integration. So because we have a discontinuity at 0, that means that by definition our integral is a limit as t is approaching 0 from the right of the integral from t to 3 of the function. And this function can be written just as x to the negative 3 half, and that means that on the interval from t to 3, where the function is continuous, we can use the fundamental theorem of calculus, and we just need an antiderivative. Because it's a power of the variable, we just need the power rule, so we have x to the negative 3 half, and antiderivative is going to be x to the negative 3 half plus 1, that's negative 1 half, divided by negative 1 half. So we obtain this function that we need to evaluate between t and 3. The negative 1 half at the bottom is really negative 2 at the top, and x to the negative 1 half is 1 over root x, so we can rewrite this as the limit as t is approaching 0 from the right of the function negative 2 over root x evaluated between t and 3. And so that gives us, when we plug things in, just 2 over root t minus 2 over root 3. And we're looking at the limit as t is approaching 0. As t is approaching 0, root t is approaching 0, and therefore 2 over root t goes to infinity. The other term is a constant, therefore the limit is infinite. And what that means is that our integral is divergent.